Okay, thanks very much, Surekha, and for inviting me. And it's certainly an honour to give some talks under the heading of Leonard Jimmy Savage. I thought I'd spend a couple of minutes saying what I've discovered about Jimmy Savage. First of all, his name, as you might have seen, it's Leonard Jimmy Savage. Well, apparently he was in the hospital for a few days after he was born before his parents named him, and the nurses started to call him Jimmy, and it stuck. So even although that wasn't what his parents originally called him, that's what everybody became to call him. He's certainly known as a very powerful scholar and a powerful personality, and he's a big contributor and advocate for subjective probability, expected utility and Bayesian statistics. And I thought I'd just read you a quote from Milton Friedman about him. Milton Friedman writes, "Jimmy is one of the few really creative people I have met in the course of my intellectual life. He has an original, independent mind capable of throwing new light on whatever problems he looks at. He also has a wide-ranging curiosity. In whatever fields he turns his mind to, he gets new insights, ideas and approaches. Here is one of those extraordinary people of whom there are only a handful in any university at any one time." So I think that's some nice words from someone else who's quite famous. As you can see, he had a few problems early on. He had trouble getting into university, and he had bad eyesight, and that led to him causing a fire in the chemistry lab. And so he then switched to mathematics because his mathematics professors didn't want to lose him. I think I can tell you two ways, probably lots more that mightn't be known to me, but two ways in which he's influenced my life. When I was an undergraduate, I studied agricultural economics in the mid-1960s, and that was when Savage's stuff was really having an impact. And in my agricultural economics department, there was some strong subjective probability, expected utility kinds of people in farm management area, people like John Dillon and Jock Anderson, and I think they had an influence on some of my thinking. A more recent incident, about 2 weeks ago, just before the third cricket test between Australia and India, I went down to my local betting shop, and the odds that they were giving on India winning the third cricket test were about 7-1, and that translates into a probability of 1/8. And so I think what Savage would say is, if you think the probability that India will win the third cricket test is higher than 1/8, you should bet some money. So I lost $5. Okay, what I'm going to try and do is talk about the seemingly unrelated regression model and talk about it in such a way that I hope will introduce a lot of Bayesian concepts that I hope you'll appreciate can be used more generally than just in the seemingly unrelated regression model. But I think the seemingly unrelated regression model is a good vehicle because I think it's a model that's very commonly used. It has a wide range of applications, and it also brings with it a lot of the elements of modern Bayesian econometrics. The structure of my talk is that I'm going to do a bit of theoretical stuff, and then I have 4 applications I'm going to talk about after that. Now, I'm not quite sure how I'll be dividing my time, and I'm not quite sure how much I'll get whether I'll get through everything I've prepared, but we'll see how we go. And you don't have these transparencies yet, but you will get them. So Surekha has them, and they will be copied and distributed before the end of the session. So there's no need to write all these things down. You can just sit back and enjoy. That's what a Japanese professor used to say to us. Say to me, don't write anything, just sit back and enjoy. Okay. Some of this will be repeating some of what was said by Arnold and Surekha earlier. First thing I think is to recognise that we can express information about something we don't know or don't know exactly in terms of a probability distribution. So that's an important point. If we want to talk about things like parameters in models, then we can express the uncertainty about a parameter in terms of a probability distribution. Other things of interest are, say, functions of those parameters. Now we'll see some of those in some of my examples later on this afternoon. Some of them will be, say, a Gini coefficient, elasticities that are functions of parameters in a cost function, and various other ones. Future values of random variables. If we're interested in prediction, then we want to be able to express what we know about future values or of a random variable in terms of a probability distribution. So they're the, to me, that's the sort of starting point in Bayesian inference, is recognising that that's what we want to do. And we have two kinds of these probability distributions. We have prior probability distributions that we set up initially, and we have posterior probability distributions after we add some information. And in general, when we're doing some kind of study or we want to make inferences about something, then it's the posterior density function that we're after. It's our ultimate objective. Or it could be a predictive distribution if we wish to predict. Now you've seen Bayes' theorem. I've summarised it again there. We've got some unknown parameters of interest that we collect into a vector theta. We've got a prior PDF on that. We've got a density function for the observed data, which is algebraically equivalent to the likelihood function. And something Arnold mentioned this morning, we usually assume we know that. He's gone into the method of moments, into studying method of moments to try and overcome situations where we don't feel comfortable about making an assumption like that. Posterior PDF, what we know about theta given y has been observed. And the last component that we typically assume into a proportionality constant, the marginal or predictive PDF for y. So I already mentioned this, but if the objective of our study is to collect information about some parameter theta, then our objective is to find this posterior PDF. So the steps we need to go through are to specify a model and the likelihood function, specify a prior for the parameters in that likelihood function, use Bayes' theorem to find the posterior PDF, and then this fourth bit, and that's often the tricky bit, and that's what we'll be spending a lot of our time on, is expressing the information in the posterior PDF in a way that we find is convenient. And how do we do that? Well, we might want to graph the PDFs, posterior PDFs of individual parameters, or we might want to do it via summary quantities such as the mean and the standard deviation of a posterior PDF. So this is the bit that we will spend a bit of time on. And this one's devoted to that idea. First of all, if theta is a vector of parameters, and it usually is, then what we've got to do if we want to get the PDF for just a single parameter is find the marginal posterior PDF for that theta, which theoretically means integrating out the remaining parameters in that from that PDF. Now, if that's not possible, if it's analytically too difficult, then what we can do is draw observations from this joint posterior PDF, which is equivalent to getting observations from the marginal posterior PDFs. And what we'll look at soon is what then we can do with those observations that we draw, and we'll also look at how we can draw them. And a couple of possible ways here are importance sampling and various Markov chain Monte Carlo algorithms, two of which I've mentioned, Gibbs sampling and Metropolis-Hastings algorithm, but there are various versions of particularly the Metropolis-Hastings algorithm that can be used. Now, often where I mentioned some of these things earlier, often we're interested not in theta itself, but functions of theta. And here's some examples. Consumer surplus. We might estimate a demand curve, but we might be interested in the area under a section of that demand curve, or in other words, an integral between a couple of values. The Gini coefficient after estimating a Lorentz function. That too is a function of an integral of the Lorentz function. Input elasticities after estimating a translog cost function. Household equivalent scales after estimating Engel curves with demographic factors. So if we want to judge how much a household spends on food or needs to spend on food to live in some predetermined comfortable way, then that will depend on the demographic makeup of that household, and these equivalent scales are designed to put different sized households on a comparable basis. And these are all examples that I will be dealing with before the week's out. Now, if we're interested in these things, how can we obtain them? Well, if mathematically tractable, we can do a transformation of variables from theta to the function of theta that we're interested in. However, if it's not mathematically tractable and we're drawing thetas, drawing values from this distribution, just using a computer, then we can also compute draws of any function g of theta and use those draws to estimate things. What else have I got here? And in some of the work I've been doing, although I'm not sort of reporting on this today, if you're doing Bayesian model averaging and your different models are expressed in parameters that mean different things, but you want to put the same kind of prior on each model, then you might want to put prior on, say, elasticities rather than model parameters. And so you might want to transform your thetas back to some other parameters, phi say, and put the same prior on those before you proceed with a model averaging setup. And in prediction, which I haven't mentioned yet, if you're interested in predicting, then you're interested in getting this density function, in other words, a density function that conditions on your past observations but does not condition on theta, which you typically don't know. Doesn't condition on those parameters. And the way you do that is to average out or integrate out theta from the joint density, and a convenient way of viewing that is an average of these conditional densities conditional on theta. If you're a sampling theorist, typically what happens is you use this to predict and put an estimate of theta in there and condition on that. So you can view a Bayesian predictive density as an average of these possible conditional ones averaged relative to what you know about each value of theta. Now again, if you can't do this integral, you can still generate predictions, and so you can still get a predictive PDF which you can go ahead and use to estimate. Okay, that's my background, and what I'd like to do now then is to talk about it in relation to the seemingly unrelated regression model. So a seemingly unrelated regression model consists of a number of equations, linear for the moment, but later on don't have to be. These are characterised by having error terms that in the same time period are correlated over equations, or if you've got cross-sectional data, you may have each equation, you may be looking at, say, a number of households. You may have demand for food, clothing, housing, other things for each of those households. So this could be the number of equations for a given household. And in those circumstances, errors for different equations within the same household would be assumed correlated. So if it's pure cross-section data, it's errors in the same household or the same firm are correlated. If it's combined time series and cross-section data, then it's contemporaneous correlation between errors in the same time period. We can stack these equations in what's become the typical textbook way, and into one sort of big superlinear model like this. We assume our error term follows a normal distribution, and this covariance structure or specification here allows for these cross-equation correlations, but no serial correlation. Our likelihood function. Now our likelihood function we can specify in one of two ways. Each is convenient for doing different things. The first one here is more comparable to the linear model as we know it. And the second one is what has been more common in multivariate statistics, but is a very convenient form for a lot of things we're going to do. And this A matrix here, which is a new addition, it is like a matrix of residual sums of squares, or cross products of sums of squares from the different equations. And so an element of this A matrix is defined like this, but notice it depends on beta. So I haven't put any estimates in here at this stage. It's a function of beta. Now, what about I haven't been checking to see that I get all this in, but I'll check on this one's a long one. For a prior PDF, I'm going to consider two alternatives. One is this first one, which is a standard diffuse or non-informative prior for this problem. It's the one that Jeffries has suggested, and it's the one that most people use. And then I'm going to use another one, which is what I call non-informative with inequality constraints. So what I'm going to say is there are a lot of circumstances where, from our economics, we have information on inequality constraints. And so I'm going to look at these two different cases. And what are examples? Well, sign restrictions on coefficients. We know a coefficient on price in a demand equation should be negative, for example. Concavity and monotonicity in a cost function. We'll see some examples of that later. But there are properties of cost functions that suggest certain inequality constraints hold. Relative magnitudes of household equivalent scales. So we know that a household with 2 adults needs more food than a household with 1 adult, and things like that. So we can use that sort of information as well. Now I'm going to write a non-informative prior with inequality constraints by introducing notation R for a feasible region, and this indicator function, which is equal to 1 if beta lies in that feasible range and 0 outside. And then my prior can be written simply by adding the indicator function. Should be proportional to here, I guess that's an error. Now, why use non-informative priors? Well, one important fact about non-informative priors, I think, which it wasn't mentioned this morning, is their objectivity in reporting. If I have my prior and I do a bit of research, you mightn't like my results because you mightn't like my prior. But if I introduce a non-informative prior, or even one with inequality constraints, then I think I'm in a better position to convince you that you could have a prior like that too. Or if you don't, you could revise what I've got according to your prior. Okay, if we use Bayes' theorem and we combine this prior with the likelihood function, what do we get for the posterior PDF? Well, you'll notice it doesn't look all that different from the likelihood function. The only difference is we've got some extra powers of the determinant of sigma, and I've now also got this indicator function that says this is only defined where in the feasible region for beta. And I can write it 2 ways, just like I wrote the likelihood function in 2 ways. And I can think of this as an appropriate specification for both priors. It's just that when I'm using the non-informative prior without any inequality restrictions, I can have the indicator function always equal to 1. Okay, now what do we want from this joint posterior? If you just look at that, then of course, suppose you derive that, which means you have some numbers for y and x, then that's not going to be all that meaningful to you by itself. So let's suppose we're interested in some of the beta ik, and possibly all of them, which will be the usual case. The subscript I refers to the equation, the subscript k refers to the coefficient in the ith equation. And what would we generally like to do? Well, we might like to graph a marginal PDF, posterior PDF for that coefficient. A graph indicates the regions of highest probability and so on. Or if we've got a whole lot of these, drawing too many graphs might be a bit laborious. We might just be happy to report means, say, and posterior standard deviations, which are defined in this one. How do we get those? Well, marginal posterior PDFs, means, standard deviations are all defined in terms of integrals or relating to the joint posterior PDF. So the question then becomes, can you do the integrals? And sometimes you can, sometimes you can't. And what I've indicated here is, generally for this model, you can't. But we can go a little way. And so what I'm going to do now is indicate what we can do and then where we can go from there. Now, first of all, we can get the conditional posterior PDF for beta given sigma as this multivariate normal, or if we've got inequality constraints, it becomes a truncated multivariate normal. How do we discover that? How do we get that? Well, we go back to our, where did I put it? We go back to our joint posterior PDF, and in this particular case, we think of sigma as being given, fixed, and then we see how we can rearrange this and whether it's recognisable. So it's a little bit of algebra involved, and we get this as a multivariate normal. We can, okay, that's all I've got on this one. Now, beta hat in this is your typically generalised least squares estimator, so if we're assuming we know sigma is known, it can be found. And from a sampling theory perspective, this is more or less the Bayesian equivalent of the way the sampling theorist would do things, except the sampling theorist would put in some estimate, sigma hat, maybe obtained from OLS residuals or after iterating to the maximum likelihood solution. Now the conditional posterior PDF for sigma given beta is, after doing a similar thing for sigma regarding beta, treating beta as fixed, you can write that like that, and you get this density, which can be recognised as an inverted Wishart. If you've never done inverted Wisharts, it's like you get a chi-squared distribution, but you get a multivariate version of that, and then you invert it. So what have we done? We can show we can get the conditional PDF for beta given sigma, we can get the conditional PDF for sigma given beta. Can we get any marginals? We can get the marginal for beta by integrating out sigma. So it is possible to integrate out sigma, and if you do, you get the determinant of this residual sum of squares and cross products of of residuals, sums of cross products of residuals in this matrix A, its determinant, and again it might be restricted if you've got inequality restrictions. This one, though, is not something we can get a handle on. This is not a recognised PDF that we can look up our textbook and say, oh, this is the normalising constant, or this is its mean and variance. So it's a little bit harder. Thought it was a kookaburra. Okay, so suppose now then that we recognise we can't do all the integration we need to get the marginal posterior PDFs that we need. What can we do? Well, as I said when I was talking generally, we can generate observations. How we use these I'll talk about soon. But for the moment, let's see how we can generate observations. And I'm going to say a couple of words about Gibbs sampling, and and then a couple of words about one particular Metropolis algorithm. Now, Gibbs sampling draws from the two conditional PDFs in an iterative way. And it's worth recalling that we know the posterior PDFs for these. These are recognised forms. You can get your computer to draw observations from those without too much trouble. I've got here providing any truncations that might be present in the multivariate normal are not too severe. What do I mean by that? Well, one way of drawing from a truncated multivariate normal is to draw an observation from the non-truncated version, and if it's feasible, you keep it. If it's not feasible, you throw it away and draw again. Now, if your truncations are a bit too severe, you may be drawing forever before you get a feasible one. And if you think about that a little bit, that's not very hard to happen. Supposing you've got, say, 4 coefficients and you want them all to be positive, and suppose there's a 0.5 chance that each of them is positive without the restrictions, then the probability of one or more of them turning out negative can be quite high. And so even although you might have individual inequality constraints that you think by themselves are not so bad, when you can put them all together, it may be very hard to draw observations from that truncated normal in this normal accept reject kind of way. There are other ways of drawing from truncated normals that can get over this problem. What I've tended to do in my research is to go for the Metropolis-Hastings algorithm when these things are what I've called too severe. This already sort of says what I've said a little bit, I think. Given a couple of starting values, sigma 0, and, well, no, sorry, you only need a starting value for sigma, then we can draw an observation beta from this conditional density. Given that observation beta I say, we can substitute that into the inverted Wishart, condition on that for the inverted Wishart, draw another sigma, put that one back in here, draw another beta, and keep on going. And if we do that, then what Markov chain Monte Carlo theory suggests is that after we take a sufficiently large number of draws, then the draws obtained this way can be considered draws from the marginal densities, not just the conditionals. And the point at which that occurs is the point at which we say the Markov chain has converged, and we can then use those draws or the ones that have occurred after convergence, to estimate the quantities we want. Now, that naturally raises the question, how do we know when we've converged? And well, you can graph the output as it comes out, and typically if it's wandering around everywhere, you should be worried. But if it tends to look as if it's from some sort of stationary distribution, then that suggests convergence. But there are all kinds of diagnostics that have been suggested in the literature, and there's even been a web page set up to discuss convergence of Markov chains. So one can look at all those things. Now, a further point here is the draws produced in this way will be correlated. They're not independent draws from some distribution that are needed, that we're used to it when we study elementary statistics. These are time series draws, if you like. They're correlated draws. And that typically means that we need much bigger samples than we might otherwise need if they're independent to get accuracy of estimation. That's one way then, Gibbs sampling of getting some draws from these distributions. And you're probably wondering, what's he going to do with these draws? Be patient. Let's talk about another way to get draws first. And one can use a Metropolis-Hastings algorithm, and we can do that on the marginal density for beta. So even although we don't know, we know it's, all we know about this is the kernel of its density function. We don't know the normalising constants or its moments, but we can still use this algorithm to draw observations from that density function. And when might we want to do this? Well, we might want to do it if our inequality constraints are too severe, like I mentioned before, or if we've got nonlinear equations, we can still do this one where we can't do the Gibbs sampler. Now there are lots of different kinds of Metropolis-Hastings algorithms, and this is the one that I've tended to use the most, and it's because it's a relatively simple one, and I've found in most cases it's worked okay. Not all the time, but most of the time. And it's what is called a random walk chain. And what you do is you start off from a particular point, and then you change your value a little bit. Or you could change it a lot too, I suppose, but you draw a value I'm talking in terms of betas here, not thetas, aren't I? So that should be a beta. You've got some starting point here, say beta 0 when I is 0, and you draw from a normal, say, doesn't have to be a normal, but and you draw what's called a candidate value. So you move away from that value a certain distance. And then, I'll draw a little picture here. Say this is my density, and say that's my beta I, and then I draw a particular value, say beta star, and that's called a candidate. Now I have to check whether I want to accept that candidate, and what I do is I compute the ratio of the density at the candidate to the value of the density at the previous value. And if it's higher, so if you've gone uphill like this, then this is a more probable value and you accept it. If it's down here, so you've gone downhill a bit, then you accept that value with probability equal to this ratio. And so you can do that by I haven't put all these steps up yet. I've got more of them later. But anyway, you'll see that in a minute. So you accept that with probability equal to that ratio. And if you don't accept the new draw, then you set your new value equal to your old value. And I mean, I can't prove to you here that this works, But I hope what you can see is that by doing this, you're going to get more values in this region of high probability, and you're going to get less values in regions of low probability. And it can be shown then that if you do this process, if you follow this process, then these can be viewed as draws from the marginal posterior for beta. Now again, this is subject to the same kind of comments as I made about the Gibbs sampler. You have to have a burn-in period before convergence, and then after convergence the draws can be viewed as draws from that density. Now, as I said at the beginning, that particular algorithm is an easy version of a Metropolis-Hastings algorithm, the random walk. A more general one introduces this function here, which is the transition density function for drawing a beta star given a beta I. And there are different kinds of transition densities recommended in the literature, different ones which guarantee convergence quicker and these kinds of things. In the algorithm I mentioned, these two things are symmetric and they cancel out. But if you want to go for a fancier one, then you can do these kinds of things. And there's a lot of papers in the literature about different algorithms that work better in different situations. And I said that already, so you do have to worry about convergence and burn-in and so on here. Okay, we've got all these observations. What do we do with them? What do we do with them? And so let's go back to where we started. We said what we're interested in are marginal posterior PDFs, graphing those marginal posterior PDFs, getting their moments, their mean and standard deviation. What we've got instead is a whole lot of draws from these distributions. And these may be draws beta 1 to beta m, say, from the Metropolis, or they could be joint draws, beta 1, sigma 1, and so on, from the Gibbs sampler. Well, what if we want to graph? What if we want to graph a marginal posterior PDF? We can simply put all these observations. Typically, we would have thousands or tens of thousands of these observations. We can put them in a histogram, and we can simply join the midpoints of these histograms, of these intervals of the histogram, and that will trace out an estimate of your PDF. It'll probably look a little bit jagged. I'll show you some jagged ones later on. You can put this output into kernel smoothers and that kind of thing if you want to make it look a little bit smoother. I tend to just leave mine unsmoothed. If you want the mean, what can you do? Well, you can do one of two things. You can, if you want the posterior mean, you can just get the sample average of all the draws you generated, and that's your estimate of the posterior mean. Alternatively, you can use this result that the expectation of a conditional expectation is the expectation of the marginal, and I've got two ways to estimate the posterior PDF. The first way is to draw a histogram and put all your observations in classes. The second way is to average the conditional posterior PDFs. So let's look at what I mean by that. If you've got Gibbs sampling output, and if this is a normal, if this is a univariate normal, as it will be if you've got no truncations, then you know the density function for this univariate normal. It's a standard normal distribution. And what you can do is you can take a grid of points of the beta ik all along here, and at each point you'll have a whole lot of marginal distributions, conditional distributions, sorry, might look like that, say. And then at each point you can average these. So what you're doing is you're averaging the equation for this density over all possible values of sigma that you've drawn. So you don't actually use the beta output to do this. You've got, or you might like to use the beta output to find the minimum value and the maximum value for setting up your grid, but you've got these equations for these conditional densities. You can set a grid of points for the betas and average those conditionals to get a single point on your marginal for each point in that grid. And if you do it that way, you will typically get a very nice, smooth, accurate marginal posterior PDF. But of course that depends on you knowing this conditional. So that what you're actually doing when you do that, you're estimating this integral. So you're in fact estimating that integral by drawing from this and averaging that. Okay, so that's drawing pictures and drawing graphs of your posteriors. Now the means, which I jumped to and didn't look at my slide carefully enough. We can average the individual betas, and I've just seen another typo. That should be beta ok there. We can average the individual draws, or again, just like with the graphing the averaging the conditionals, we can average the conditional means. And so this is how we would average the conditional means. Notice the conditional means just depend on sigmas. So it's like averaging every possible generalised least squares estimator over every possible sigma, but the sigmas will occur in proportion to the probabilities that related to them. Now what about the posterior standard deviation? Well, let's talk about variances, although I prefer to report standard deviations. The posterior variance can simply be estimated as the variance of your individual draws, or again you can use a conditional relationship, but in this case the variance of your marginal posterior is equal to the average of your variances of your conditional posteriors plus the variances of your conditional means. That's a bit of a mouthful. But notice this element will be like this thing here, your standard generalised least squares covariance matrix. This thing here is your generalised least squares estimator, and what you're doing is you're looking at the variance of that relative to the marginal mean and the average of your variances. Now, typically when I've done this, and I've done it both ways, these things are almost exactly the same. So it does work. Now, another question is, if you do all this, and how accurately have you done it? The question is, how how close do you know you are to the true posterior moments that you're trying to estimate. Now, you can always improve the accuracy by generating a bigger sample. We're using our computer to generate a sample, so we can generate one as big as we like, as long as we've got enough time. And we can't just get an ordinary formula like sigma over the square root of m, like we do for independent sampling, because these observations are correlated. But we can use time series methods to get an estimate of the variance of the mean. And this is one that John Guicke has suggested, and I used in a comment on his paper. This is a bit of a computing mess, but you can program that up and do it without too much trouble. Okay. Quite finished the first part here. There are a couple of extensions here that what I've called extensions that I wanted to mention, and these are things that I've come across in some of the examples, and so I just wanted to point out that you can handle these things. And the first thing is cross-equation restrictions. What happens if you've got cross-equation restrictions on your coefficients, as we often do in demand systems and production systems. And what you can do is basically substitute out those restrictions, and you can do so in this in this kind of way. If they're linear restrictions, I'll quickly go through this. Partition X according to the number of restrictions. Partition your restrictions written as r beta equals little r, such that r1 is non-singular. Partition your coefficient vector beta into eta and gamma. Gamma are your say free parameters. Eta are your parameters that can be derived from the estimates of the gammas, and you can then get an expression for eta from the restrictions and substitute out and do your analysis on this equation where we've got y star and x star. You no longer have an x that's block diagonal as you do in the traditional seemingly unrelated regression model, but that doesn't really matter. Nothing we've done so far actually depends on x being block diagonal. If the restrictions are nonlinear, then that's really equivalent to having a nonlinear system, I guess. So if you've got nonlinear restrictions or you've got a nonlinear system, then you can proceed in this way. We can no longer do the Gibbs sampler because we can no longer get a multivariate normal for the betas, however, for the conditional, we can no longer get a multivariate normal for the conditional posterior PDF for the betas. However, we can still integrate out sigma in the same way. We still get this same A matrix, which is still the matrix of sums of cross products and sums of squares of residuals. It's just that these functions now are nonlinear. And notice I don't have any subscript on beta, which means some betas may appear in more than one equation. Now prediction, I'll quickly run through prediction because I do want to move on to the examples. So I want to imagine here you want to predict a vector of future observations y star given by an equation here that's consistent with our earlier model. You can get the conditional posterior or conditional predictive PDF for these observations that depends on your coefficient vector here, but you can average these conditional densities using your draws of beta and sigma to get a marginal predictive PDF that's free of the parameters in much the same way as we averaged conditional PDFs for beta. If we want the moments, as well as drawing a picture of the individual predictions, then we can average the conditional predictions, and then we can also find the variance of the predictive PDF by, this is the conditional covariance matrix of your predictions, and so we're averaging those, and here we're averaging the conditional, we're estimating, sorry, the covariance matrix of the conditional predictions given sigma, and it can be shown that that's equal to the sum of those two components. So just given our output from, say, the Gibbs sampler, without generating any more simulated observations on predictions and so on, we can use that output and properties of conditional densities to estimate our marginal predictive PDF. However, you could draw predictions too if you wanted to. You could go back to the original equation, and you could for a given draw of sigma that we found earlier, you could draw an error term E. For the corresponding draw of beta, you could compute that part, and that would give you a prediction. So you can get observations on your predictive density in that way if you wish, and then graph those and so on. But if you're able to use the conditionals and average the conditionals, generally you get more smoother, just smoother results and so on. Okay, I think I'll leave that that first section there. When you get a handout, you'll find I've also got a few references, not many, but just a few books that I find useful, and also a few web pages that I find useful. So there'll be a list of sort of Bayesian type web pages, and introductory and not so introductory books on Markov chain, Monte Carlo and Bayesian estimation.